immense pleasure in introducing Professor Paavo Pelkkanen, an eminent researcher in cognitive neuroscience. He is with the Department of Cognitive Neuroscience and Philosophy, University of Skövde, Sweden, and Department of Philosophy, University of Helsinki, Finland. He is particularly known for his work on mind-body studies, building on David Bohm's interpretation of quantum mechanics, in particular Bohm's view of the cosmos as an enfolding and unfolding whole, including mind and matter. Professor Pelkkanen's areas of specialization are the mind-body problem, the basis of cognitive science, philosophy of physics, the philosophy of David Bohm, and the foundations of quantum theory. Professor Pelkkanen has worked and published together with theoretical physicist Basil Hiley to address the question of the relation between mind and matter by the hypothesis of an active information within the conceptual framework of the de Broglie-Bohm theory. Professor Pelkkanen's work on mind, matter, and the implicate order, published in 2007, builds upon David Bohm's ontological interpretation of quantum theory, in which quantum processes are understood as a hollow movement in terms of implicate and explicit orders. Today he is going to deliver his talk on the topic, Does the quantum theory make room for the causal powers of consciousness? We are anxiously looking forward to hear Professor Pelkkanen. Professor Pelkkanen, please.
Right. Thank you very much for the nice introduction and also for inviting me here. A couple of little corrections. I would love to be a specialist in cognitive neuroscience, but I'm more on the philosophy side. So just as but our department has cognitive neuroscience in the end. But you know, the natural sciences have always a bit of an imperialism. So philosophy is in the back. The other thing is that some of you may, if you're awake, you may have noticed I've changed the title. And partly Stuart is to blame because he wanted that I connect with this quantum cognition. But actually it's also my fault because I got extremely interested in this over the past few months. And if that happens to a philosopher, it's great news. You know, philosophers usually are stuck with the same problems. If you get so excited that you want to change the topic, then maybe something exciting is happening here. So I will solve the problem of the causal powers of consciousness later on. I have actually a paper about that. It's a draft. If anybody wants, email me and I'll send you that. But anyway, so here goes. We go to quantum cognition, and we are going to discuss analogies between quantum and cognitive phenomena. And I will tell you a little bit also about the Bohmian program more generally. Okay. I want to start just a little bit about this because somehow I feel that as we are discussing these issues, and it connects a little bit with yesterday's themes also. When we talk about science, I think there was something that was a little bit missing when we talk about science, and that's the role of criticism. And I've just here given an example of Bohr and Einstein, where Plotnitsky points us that actually, you know, Einstein never liked quantum mechanics. And this was the driving force for Niels Bohr when he was developing it. And Plotnitsky is speculating that actually without a critic, Niels Bohr would never have gone where he actually did go to. So that's the other dimension just to be emphasized, how criticism is an important aspect of science and philosophy. And we may be afraid of criticism because we want to protect things we value. But the case of Bohr and Einstein shows that criticism, far from being destructive, actually played a key role in the development of ideas. Now we could ask, actually one could say that they actually failed to have a dialogue, which is to really understand each other. And even today, maybe physics is divided because of this, but that's another story. Okay. Anyway, so when I think in the conference like this, we are asking huge, big questions about, can we know reality? What is consciousness? We may say that standard science is wrong. We may come up with our own huge ideas and theories. But it's important to remember that everything should be open to criticism, debate. I can make any statement I want, but then I have to back it up and invite criticism from you as well. So that's just something to add to what science, this is the whole thing about Western science, is a certain kind of skeptical attitude, and everything in principle can be questioned. Anyway, we go into quantum cognition, and we're going to be questioning a lot of mainstream dogma here with some exotic stuff. There's a BBS article coming up by Potos and Busemeyer. I think Busemeyer is an economist. Potos, do you know? Sorry? Cognitive science, okay. And so there are now this, and you may have heard about this a little bit before in the conference with Brusa, but there are important empirical results concerning human decision-making and judgment. And what Potos and Busemeyer, like PB I call them, they say that these can be elegantly accounted for by quantum probability theory, while classical Bayesian probability theory fails. So this is, of course, this is sort of, this is how quantum mechanics began. We had certain things like black body radiation, which a classical theory couldn't explain, and that's why people were forced to develop a new theory. So this is very, very important, if this is true. And here are some examples. Human judgment and preference often display order and context effects, violation of the law of total probability, failures of compositionality. About order effects, there is an example given that if you ask the questions, is Bill Clinton honest, and then ask, is Al Gore honest, people will answer differently depending on which order you ask those questions. For Clinton, it's more beneficial to ask first about Al Gore. Then he'll get a better grade of being honest. So that's an example. Now, these kind of effects are very difficult to model with so-called classical models, classical probability. Whereas quantum probability, which has various features, you can superpose, and also you have kind of the order of making experiments is important in quantum theory. So actually the Potos and Busemeyer show beautifully in their article how quantum probability theory could account for these kinds of effects. Okay? And they say that quantum probability theory is potentially relevant in any behavioral situation which involves uncertainty. And of course, we could say, what else is life than uncertainty, right? Quite often, anyway. So here we see the importance. Okay, now we have a success in modeling, and that raises a question: how can it be that quantum probability theory, which was originally developed to account for quantum physical phenomena, could possibly be able to account for cognitive phenomena? I mean, people might think, well, these are the little thingies, the atoms and the atomic domain, nuclear domain, and then we have the mind. I mean, that must be some emergent macroscopic whatnot property. I mean, why should they be? How could you ever use a theory developed for the, if you like, for the micro nitty-gritty to describe the cognition? And this is actually not addressed. They remain somewhat agnostic there in their paper, but they imply that the reason is because some cognitive phenomena are analogous to quantum phenomena, meaning they're similar in some relevant way. So it seems that some cognitive phenomena and some quantum phenomena are analogous, but this gives rise to a further question. Why are they analogous? It could be a mere coincidence. That's, of course, whenever there's interesting data, correlations, somebody says, well, it's a coincidence. But then, quite often, science actually starts from observing some correlations and then asking, well, why are these things correlated? And that might lead to a discovery of a mechanism, a common mechanism, or they could be the aspect of the same thing, or there are various possibilities. And now, you see, this is an old idea, which also Potos and Busemeyer acknowledge. And following Niels Bohr, David Bohm suggested already in 1951 that there are a number of close analogies between quantum processes and our inner experiences and thought processes. And he also speculated about the underlying reasons for the existence of the analogies. Again, following Niels Bohr, they already speculated about the brain. So these were, if you like, the pioneers of quantum cognitive neuroscience, or whatever you want to call it. And so to understand the historical roots of quantum cognition, it's useful to consider these ideas. And I actually wrote an article about this, published 2004 in an excellent series by which Maxim Stamenov, who is here, is editing. But I'm afraid nobody has read the article, so not very many people anyway, so I'll be actually quoting myself here because a couple of times, which I usually don't do, but I think this whole quantum cognition thing, in a way, draws attention to some of this stuff, right? But before discussing Bohm's analogies, I want to give a short overview of Bohm's various programs, as this may also be relevant to understanding cognition and even conscious experience. So that connects a little bit of what I actually promised to do in this talk. So anyway, here's Bohm, and it says Reds in the newspaper. I don't know where it's taken, but this was probably somewhere in the 50s, 40s in the States. And just a few words. I mean, I think he would generally be considered one of the best physicists of his generation, and he did so-called mainstream physics like plasma physics, which laid the ground for solid-state physics, and then they are known for the so-called AB effect. But he's also known for his work on the interpretation of quantum theory. And just to kind of summarize, you could say he was a complex intellectual who changed his views, scientific, philosophical, political, spiritual, and then worked with many different programs which he later tried to interrelate. And that can be confusing to people. I think I probably first met myself Bohm in 1980, and I read Holism and the Implicated Order, but it took me 5 years to realize that Bohm had actually two different theories in the book, so you have to kind of divide and conquer if you're Bohm, if you want to understand him. But anyway, I'll just give you some very quick. And that, of course, means that there is no single Bohm. I mean, some of his ideas are actually in complete contradiction with each other. You can then reconcile them, like subsume one on the other, but, of course, then maybe you don't have to do that. Just let them live their lives. Now, in this 91, he wrote the textbook Quantum Theory, which is one of the best. Einstein felt that was as good as you could do to the so-called Copenhagen interpretation. And he actually used the version there. Bohm thought at the time he was presenting Niels Bohr's view, but realized later that it was closer to that of Wolfgang Pauli. It actually showed in the response because Pauli was enthusiastic. Bohm sent the book around. Bohr never bothered to reply. And one of the key ideas there, which connects what I think Deepak was saying yesterday, was that the quantum system was seen in terms of incompatible potentialities. So you can either measure position or momentum, but not both. So in some sense, they are potentialities. Heisenberg later uses also the concept. Actually, usually people think it was Heisenberg, but who got it, but Bohm actually had it there in the 51 book, quite well developed already. Now, you see, in 1952, they called this B52. It was like a bomb to the physics community. After many discussions with Einstein, Bohm published an interpretation of quantum theory in terms of hidden variables. And this thing has many names. There's a de Broglie Bohm theory, pilot wave theory, causal interpretation, Bohmian mechanics. Bohm himself liked the ontological interpretation when in his older days, because he felt the real thing was, can we have a quantum ontology? Can we, what is quantum reality like? People talk a lot about observations and measurements and predicting probabilities, but what about what is there? Can't we even have a hypothesis? So that's what this was. That was the first consistent story about what's the nature of quantum reality. And you see, while initially dismissed, this interpretation is today one of the main candidates. So if you see the entry Bohmian mechanics in the Stanford Encyclopedia of Philosophy, that'll give you also criticism and the whole thing. But anyway, I mean, I think anybody, the reason why it's important, because it does retain some of the, if you like, classical features. We can have objects, we can have movement. For example, this is just quickly to show how it does in the two-slit situation. But the model says that the electron is a particle accompanied with a new type of quantum field which guides it. So that's why it's called a pilot wave. It's a bit like if you have a ship guided by a radar wave. So you have like a particle-like thing, and then you have a guiding field. And this is just to illustrate a little bit. It's a bit of a hype even with the Bohm theory. And one of the supporters is Mike Towler in Cambridge, and he actually gave a talk which calls the return of pilot waves, or why Bohr, Heisenberg, Pauli, Born, Schrödinger, Oppenheimer, Feynman, Wheeler, and Einstein were all wrong about quantum mechanics. When he sent this to the Physics Society, they return it and say why Bohm was right, because they felt this was too strong to say that. But anyway, he wanted to have his way. And in some sense, you see, this is what the Bohm theory did. It's a counterexample to all the claims in quantum mechanics that you cannot have this, you cannot have that, it's impossible to have this, it's impossible to have that, because he actually showed that you can have it, but Bohm we cannot test it directly, we cannot prove it. So in that sense, it's just a hypothesis, but still, people were saying you can't even have the hypothesis, and there they were all wrong. So we are resolving this wave-particle duality by postulating that an electron is a particle always accompanied and guided by a new type of field. And in the two-slit experiment, the particle goes through one of the slits and then appears at a point in a photographic plate. There should be another plate. And you see, because in the two-slit, you think the electron leaves as a particle, it comes as a particle, but yet there is this kind of so you have to account for that. And this explains why we see an appearance of a spot. And note especially that there is no need to assume a collapse of the wave function. I mean, there is a kind of an effective collapse in the Bohm theory because the particle, it has to, when you make a measurement, only one part of the field is connected to it. So the other parts become inactive. Bohm called it inactive information or even passive information. So but it's strictly speaking, nothing is collapsing. The electron just loses all the information that it has in a quantum state. Okay, the way it works here is that the particle goes through one of the slits, the accompanying field goes through both slits, interferes afterwards, and guides the movement of the particle so that the particles collectively, spot by spot, build up an interference pattern. So the field knows whether you have one or two slits open, whatever else is happening in the environment, and then that information is fed into the particle. And in my view, this is the true quantum information, ontological information. What people call a quantum information is usually more of an epistemic thing. But anyway, nobody cares about this idea. So Stuart is the only one who invites me to speak about it. So that's why I'm here. So anyway, how does the field guide the particle? The field gives rise to a new type of potential energy, which Bohm called the quantum potential. And here we can say at the potential as two-slit, we can visualize a potential like a mountain. So the electrons are coming from the two-slit toward you. If it was classical physics, there would be nothing there. They would go in straight lines. But they actually encounter this potential. So you can see that that will profoundly affect depending on where the electron is coming. And all that leads then to these trajectories and to interference patterns. So this was not supposed to be even conceivable. But that's what happened. That's why it's B52. That's why it's the bomber plane for the Copenhagen interpretation. Of course, they can protect themselves because we don't observe, but some of you may have noticed people talk about weak measurements today, and we are actually observing average trajectories. And Basil Hiley is right now in London engaged in an experiment when they're trying to do this with fermions. So who knows what will come out of this. But thus far, these are purely hypothetical. Only things we can observe are the dots appearing on the very right-hand side of the screen. Okay, anyway, so there's Bohm's happy as later on in his life. Now, there's another thing that many people, perhaps especially in the new age, know about. This is the Implicated order program. Now, and here's just Bohm's own words. He says, because the response to the hidden variable interpretation was so limited, and because I didn't say clearly at the time how to proceed further, my interest began to turn in other directions. And he mentions order. He studied a correspondence with an artist, which is a huge. I've edited the first volume. It's very fascinating as it goes. And then also he became interested in language. And for example, admits that he began to understand Niels Bohr only after understanding through Schumacher, maybe some Wittgenstein. And Niels Bohr is a very difficult thinker to understand. But apparently Bohm managed to do it after he wrote a book about it. So these two interests, order and language, led to a paper on order in physics and on its description through language, where Bohm compared and contrasted relativistic and quantum notions of order, leading to the conclusion that they contradicted each other and that new notions of order were needed. And that's how you come into this implicate, explicate. And this is a kind of a program that that's in some ways similar to string theory or quantum low gravity. It's a general framework in which you hope to unite quantum theory and general relativity. So it's much, if you broader and bigger than the 52 hidden variable theory. Anyway, now we go back to the analogies. That was just a quick look at the whole picture, and we do a little bit of more nitty-gritty. Now, so when Bohm started to talk about the relevance of quantum theory to mind already in the textbook in 51, so you could apparently do it then if you were smart enough. See, note here, these ideas were when he was still thinking within the usual Copenhagen invitation. Now, this might make them more palatable and also directly relevant to recent work on quantum cognition, because that actually is pretty much within the usual interpretation. But however, Bohm's other programs, hidden variables and implicated order, are also potentially relevant to cognition and perhaps even consciousness. And I there refer to my book with the Springer, where I discuss both of them. So I won't talk about them today. All right, so which analogies between quantum and cognition did Bohm point to in 51? I've labeled them. I mean, he doesn't do that, but the first one connects to uncertainty principle of incompatibility, second, contextuality, and then so what we might call quantum classical modes of thought. And we'll go through them. Okay, so watch this first analogy, incompatibility of observation. Now, if a first person tries to observe what he's thinking about at the very moment that he's reflecting on a particular subject, he introduces unpredictable and uncontrollable changes in the way his thoughts proceed thereafter. Okay? Now, if we compare the instantaneous state of a thought with the position of a particle and the general direction of change of that thought with the momentum, we have a strong analogy. And of course, this is a kind of connects with the order effects you have and various other, like asking a particular questions will affect how a person will answer the next question. Trying to get certain kind of information will affect other kinds of answers. And the second analogy we could call contextuality. And here is again, this is Bohm PowerPoint, so it's almost direct quotation. So if a person attempts to apply to his thinking more and more precisely defined elements, he eventually reaches a stage where further analysis cannot even be given a meaning. So we could say that part of the significance of each element of a thought process appears to originate in its indivisible and incompletely controllable connections with other elements. If you like, there's a kind of connection to it's always the context. And you can see that with language. Language, where I've connected with Brusa's quantum-like lexicon and also Art's quantum-like concepts. So this is with meanings of words. I won't read all of them aloud. And finally, the analogy. So what about quantum mechanics? Well, we have in the Copenhagen view, especially, you think that some of the characteristic properties of a quantum system depend on indivisible connections with surrounding objects. So the idea here is that we have elements. They can have certain characteristic properties. So individual words have meaning, or an individual electron exhibits either a wave or a particle nature. But they have those properties partly in virtue of the relations they have with other elements, and change the relations, and you may profoundly change the characteristic properties. So, for example, an electron that just exhibits a wave-like property may suddenly exhibit a particle-like property if it is made to interact with an apparatus that measures its position. And then this is something that I've developed myself. We have in philosophy so-called meaning holism, which says that the statement that previously seemed, or we could, this implies that the statement that previously seemed false may suddenly seem true if we make drastic enough adjustments elsewhere in the theoretical system it belongs to. So Quine's insight was to say that we are, in some sense, when we are testing our statements, we are actually testing the whole of science. Because you can always, if it turns out that your proposition turns out to be untrue, you can go and fiddle in your theoretical framework and bingo, it's true again. And there's a paper in the series of Maxim Stamenov that I'm referring to, where I've had to go back to and look at some of these things. And then there's a third analogy, and then which in some sense also helps to bring the three together. So we start by saying that there's a similarity between the logical aspect of thought process and the classical limit of the quantum theory. And connected to this, there's a similarity between what Bohm calls the non-logical basic thinking process and then quantum processes. And then again, if you look at the literature in quantum cognition, Aerts talks about two modes of thought. Of course, Aerts does it in a very sophisticated mathematical way, but in some ways, some of the ideas you can see already for example, in the Bohm. Now, what's the classical limit? And so we say quantum theory has a classical limit. Now, at the fundamental quantum level, movement seems it discontinues. This is in the Copenhagen view, and I guess deep down everybody agrees, right? Now, however, there's a domain of physical phenomena where Newton's laws of motion that are continuous and deterministic provide an approximately correct description. And this is, then Niels Bohr developed so-called correspondence principle. And you see, when they were making quantum theory, they realized that the laws of quantum physics must be so chosen that in the classical limit, where many quanta are involved, the quantum laws lead to the classical equations as an average. So, I mean, this is, and again, it came a little bit yesterday discussions, what's the status of the classical world. But like here again, we need the classical world when we're developing quantum theory. Otherwise, we wouldn't know what to do, how to construct it. It's a kind of a constraint. And so, and then we can reconcile the two levels by noting that the discontinuities are too small at the classical, and also that there are so many quantum processes that the deviation is negligible from the actual result. And we could say that, Bohm was, even when he was doing the 51 book, he was interested in the ontology, what's the reality like? And it becomes obvious that from the discussions that quantum theory emphasizes the indivisible unity of the world, it seems that in our everyday experience we encounter a world that, for all practical purposes, be analyzed into distinct elements. So this world is the classical world. It begins the world all of you see. And, I mean, we could worry about what is it that we are seeing, but philosophers are today converging to the view that, my God, we are actually seeing chairs there, and maybe we are allowed to think like that. So we are actually, in some sense, seeing the classical world. So enjoy it. I mean, maybe philosophers will soon tell you, no, you're just seeing your own experiences, your own qualia, whatever. But maybe you're seeing the chairs. So there's the quantum world and the classical world. Now, these worlds are not separate, but the classical world is the subworld contained in the overall quantum world. And if you like, the overall quantum world observes itself with the help of its classical subworld. Because you see, the quantum world, everything is subtle, irregular. You couldn't establish a measurement there. So we have a important place for the classical subworld. Without that, no quantum experiments. That's where we also observe them. So and of course, that's very nice. We look at it from the point of view of the universe itself. But then this is the structure of the universe. There's the overall quantum world, but within it is a subworld where measurements take place. Our bodies are there, our brains are there, but maybe a part of us, okay, it could also be in the overall or quantum. Maybe a human being is both classical and quantum, and the classical is, strictly speaking, a part of the quantum. This is the simple picture. Again, I'm putting this because these things often get very, very confused, and we forget. I mean, in a conference like this where we talk a lot about quantum mechanics, it's easy to deny the classical everyday world. And Maybe we don't need to do that. Now, in my view, the best account of this world is given by Bohm's later works. So this is the book Undivided Universe and even the 52 papers. So I was talking with Basil Hiley last week, and I told him that I had reread the Bohm 52. We are writing on a paper. And Hiley told me that he actually, even though they wrote the book 93, he said, I wonder what new things did we put into our book, because there's so much in the 52 papers. So they're quite fascinating. All right, but we go back to the analogies and start developing this analogy of the quantum classical. It's a bit more difficult than the other one. Now, he suggests that the relation between the logical process to the most general type of thought process is analogous to the relation between the classical limit and the most general quantum process. So we have like these two pairs. So Bohm implies that there is a general type of thought process in which wholeness prevails. The component ideas are not separately existing elements with well-defined meanings. These ideas do not necessarily transform according to the rules of logic, but he says that they can flow steadily and indivisibly. This is kind of, the stream of consciousness and various kinds of creative. Again, even how Deepak was describing the mind yesterday would fit in here in some respect. And again, this general thought is a process, but not necessarily a process having an order and necessity characteristic of logical thought. So this is a kind of a question about our cognition. Now Bohm said, just as the physical world has a classically describable domain, so the process of thought includes the domain of logical thought process, which we could call it classical limit of thought, if you like. And then in that limit, the indivisibility and uncontrollability between ideas that typically prevail in the general thought process have such a small effect that they can be neglected for all practical purposes. So if you go and study logic at the University of Philosophy or whatever you study, then you have to also develop your classical muscles, so to speak, in your mind. And this, if we have this classical limit of thought, it makes possible for a relatively autonomous elements, for example, concepts that classify objects to arise. In cognitive science, it would connect also to the so-called symbolic paradigm, and when we have symbols that we manipulate, we have syntax and things like that. I mean, computer science, all of this, you need that kind of, that level. It also makes possible for such elements to have causal relationships with each other. For example, those causal relationships required for an actual thinking process to proceed according to the rules of logic. I mean, if we assume that thought is a material process in the brain, and then when we are thinking in terms of logic, then somehow there has to be a necessity there. Otherwise, you wouldn't be able to do it, right? So in this way, the classical limit of thought makes logical thinking process possible. Now, it's important to know that Bohm doesn't deny the importance of the classical limits of thought any more than he would deny the importance of the classical limit of quantum theory. Like, we need the classical limit to have life, to have biology, to have brain, things like that. That came out yesterday, I think, in Chris Field. And then, logical thinking is fundamental for the enterprise of science and for thought in general. So it's, again, here, let's not, even if we discover some kind of more general quantum level, let's not throw away the classical side of things. But on the other hand, Bohm's approach implies that it would be a mistake to assume that logical thinking is the most general essence of the thought process, just as it would be a mistake to assume that classical physics reflects the essential nature of the physical world. And this underlines the revolutionary potential of quantum cognition. Okay, so here I'll summarize this part. The new proposal that comes out of Bohm's analogy is the idea that our thought process has a quantum-like aspect, and even more strongly that the basic, most general type of thinking process is quantum-like. And this is characteristic of quantum-like complementarity, or perhaps you could say incompatibility, in the sense that making one aspect of the process definite inevitably changes other equally significant aspects. And then we have quantum-like wholeness in our thought process, in the sense that the characteristic properties, for example, meaning, of elements of thought depend on indivisible connections with other elements. This would be also the contextuality. And and then there's a suggestion that the way the general thought process changes from moment to moment is also quantum-like, or it involves indivisible non-logical steps. And here, I think Bohm is taking the popular metaphor of making a quantum jump in your thinking, a quantum leap. And this was Fred Alan Wolf, taking the quantum leap. Of course, you can take it in, creativity, insight. When you get new ideas, it seems that you just get them from nowhere suddenly. I hope that would happen more often than it does, but still, some people claim, and Bohm claimed that's the way it works, so take his word for it. Anyway, so, and finally, the basic thinking process seems to have a classical limit, namely thinking in terms of well-defined concepts, including the logical thinking process. So, I would say that Bohm suggests and anticipates profoundly many of the current successes in quantum cognition. In the many experimental results, we may be witnessing the outcomes of human general thinking process, which is quantum-like and obeys quantum probability theory. Now, of course, I think if you look at it, then you can see it's different. I think what people are doing today can be in many ways richer. Ideas are different. But it's, again, it's interesting to see how you can capture some of the essential ideas even without the mathematics. And that's what Bohm did quite a lot in physics as well. It was often left to Basil Hiley to work out the nitty-gritty details, and Bohm was moving on to something else. Okay, now we move into, we've been talking about quantum cognition, and that is kind of agnostic about, are there subtle quantum effects in the neural correlates? And we might even call that weak quantum cognition. But then we have something we call strong quantum cognition. That's like something like what Stuart has been promoting, where we actually feel that somehow, like in the case of the analogies, the reason we have these analogies is because, in some sense, cognition is correlated with quantum processes in the brain, and the quantum-like aspects of cognition have to do with the quantum-like nature of the neural processes. We have many theories like that, and Bohm also, he takes that up also, and he says that if the actual, the physical aspect of thought would involve quantum processes, this would explain in a qualitative way the analogies. It would explain why the mind is quantum-like if the neural processes are quantum-like. That would be one way of explaining it. So how would you explain the incompatibility analogy? If you say, well, if the physical aspect of thought involves quantum processes, it would explain qualitatively why the direction of thought is disturbed by an attempt to define its content. And I think you could do something similar for the other similar examples. What about contextuality? Again, if we feel that the way language, for example, is implemented in the brain, or if it's implemented in some sort of quantum fields associated with the brain, or quantum-like fields, if we don't want to reduce everything. Again, we could perhaps, this would be one way of explaining those things. I think people are particularly excited. I think Bruce are there. They feel that concepts have this very strong holistic quality, and they feel entanglement is relevant there. I haven't myself looked into that aspect well enough, but that would be the exotic. That's the exotic possibility there. What about the classical limit? Again, we could say that the physical aspect of the alogical, aconceptual thought process might involve quantum processes, while the physical aspect of the logical and conceptual thought process might involve classical processes, or classical describable. For example, classical describable neural activation patterns. Again, so we could have those two systems interacting with each other, and maybe, you could have, Stuart likes to talk about the autopilot mode of the mind, and maybe some of that could be classical also, but then there could be also an underlying quantum-like, and that could be also where our experiential states lie. And and even here, you see, okay, although I have focused on Bohm, it's Niels Bohr that's in the background. So this is a reason to maybe give another look at Niels Bohr's work as well. Bohr speculated that thought involves such small amounts of energy that quantum theoretical limitations play an essential role in determining its character. So this is the idea that we need quantum theory with small energies. And okay, Bohm acknowledges that the brain obviously involves classically describable mechanisms that seem to act like a general system of communications. But he knows that Bohr's suggestion involves the idea that certain key points controlling this mechanism, which are in turn affected by the actions of this mechanism, are so sensitive and delicately balanced that they must be described in an essentially quantum mechanical way. We might, for example, imagine that such key points exist at certain types of nerve junctions. And this is, now Beck and Eccles actually made a theory like that. And actually I met Eccles 91, we had a conference in Prague where we actually discussed a little bit these models, but not, I think quantum cognition wasn't sufficiently developed at the time. Of course, we could say microtubules, I mean, it would be nice to see what Bohm's reaction would have been. But anyway, there are many possibilities today. Bohm added, it cannot be stated too strongly that we are now on exceedingly speculative ground. But anyway, I think this is another aspect of science, is that we have to speculate and come up with new ideas. Now here, before I end, we should make a sober reminder, you see, because there are various ways in which the neural processes underlying cognition could be quantum-like. There's a weaker possibility to assume that the neural processes involve no self-quantum effects, but can nevertheless give rise to quantum-like neural activity. And you see something, there was a special issue in the Journal of Mathematical Psychology, 2009, and the first article is by Barros and Suppé. Barros is not the EU commissaire, but it's another researcher. So they imply something like this when they suggest that classical interference in the brain may lead to contextual processes. They refer to experimental work according to which cortical oscillations may propagate in the cortex as if they were waves, and the simulations of the mammalian brain which show the presence of interference in the cortex. So interference as such is something you could, as we learned yesterday, that 2,000 years ago when people were putting water waves through the holes, you got interference. And so some of these probability experiments you could, the quantum cognition data could be accounted for by this kind of entirely classical physical process. But then again, the question, I think they realized that you can't do entanglement with classical physics. And that's why they actually feel that there is no evidence of entanglement in the cognitive phenomena. So they take a kind of a sober view. But still, I mean, I think it's great to see. I mean, Suppé is maybe one of the best logicians in the world, and he's not very young anymore. But it's fantastic to see that he's coming into this field. A lot of philosophers are running away, shying away and hiding somewhere when these things are discussed. But another colleague who was a colleague of Suppé's is the Finnish philosopher Jaakko Hintikka, and he's now also. Been working for 50 years, but he's excited about this, not necessarily quantum cognition, but these possibilities opened by quantum mechanics. So some of the best philosophers are with us, but not all of them. Okay, that was just a side comment. Anyway, we go back to this bandwagon, and we can say that today, I think it's probably 80 years after Bohr's suggestion and 60 years after Bohm's discussion, we see a rapid proliferation of interesting research in quantum cognition, biology, quantum computation, quantum information. And this is also now in leading scientific journals. It doesn't prove that it's true, but at least it kind of means that it's perhaps gone through skeptical, critical machinery. And I think most importantly, there is the empirical data in quantum cognition. And there's the empirical data in quantum biology. And that's how science often works. That people can have speculations, ideas, theories. Often if the theories are too far out or off the wall, people will ignore them. But if you can connect with experiments, then there's a buzz. And there may be a trip to Stockholm as well for some of these people, who knows. So, by now, we ought to realize that the scientific and philosophical implications of the above line of thought are potentially very significant, because there's a possibility of a revolution in our understanding of the mind and brain that might parallel the significance of the quantum revolution in physics. And I'll end there. Thank you.
Thank you. That was a very interesting review of the current status of what's going on and how it relates to bone. I just wanted to ask, you mentioned the classical limit of thought. And would it be, the first question, I guess, in general is, would it be fair to say that the classical limit of thought is the highly amplified excitation patterns that we actually experience consciously? And in particular, if you look at the, I think, growing evidence that analogies are all actually executed unconsciously, from Kunios's group, for example, from a neuroscience point of view, and also computational thinking about analogy would suggest that the implementation of analogies is unconscious and only the result is experienced consciously as an amplified state. Would you think that that's a fair characterization of the classical limit?
Right, that's a good question, and I should add that that again these are sort of I presented some of these ideas. Then it's another question whether they are correct. Now, my own inclination would be to say that in our conscious experience, we're actually maybe conscious experience is primarily aconceptual, and so in that sense, the quantum light dominates in conscious experience, especially with young infants. Maybe also we talk about animal consciousness, and then maybe human consciousness, especially in various experience. We can have religious experiences or sexual experiences, aesthetic experiences, and then drugs. There's a whole variety of experiences where the, if we now want to call it quantum-like, dominates, but we could call it the aconceptual experience. Whereas then the so-called classical limit of thought is that's where concepts would dominate, but then again, those things could be possibly going on, especially information processing can be, a lot of it probably is unconscious. We're conscious of a very little part at a time, but in that sense, perhaps there is hope for the aconceptual side of things. But today, people often also feel that, especially in the academia, the aconceptual mind is suppressed and the conceptual dominates. And this theme is, there are philosophers like the late Heidegger, Merleau-Ponty perhaps, they call themselves post-phenomenologists. And a colleague of mine in Finland, Pauli Pylkkö, has written a book about that. This is also in the Maxim Staminal series of John Benjamin's. So that's one of the key issues. But then again, how to answer it, we would really have to look at all these things much more carefully.